Okay, so Stokes 3. So we're computing a line integral. We got a vector field. We got a curve. The curve's parameterized. Again, you could brute force this. That'd be really tedious, really nasty. We don't want to do that. I claim it would actually work, believe it or not, but it would be super, super inconvenient. So here's the more clever way to do it. Let's draw a picture of our curve. And wow, that's going to be hard to draw a picture of. But first notice that it's periodic. Right? T goes from 0 to 2 pi, and after that, sine and cosine, they're periodic. So this curve wraps back on itself after exactly 2 pi. So this is a closed curve.
Yeah, that's what I did. I checked the endpoints and got the same values.
Yeah, exactly. And furthermore, notice that y is always equal to 5.
Yeah, that's what it's going to be.
Yeah, y is always equal to 5. So this whole entire curve lives inside of this plane where y is equal to 5. So there's the plane where y is equal to 5. And this curve, I don't know exactly what it looks like, but it lives inside of that plane. There's our curve. Cool?
Yeah.
Okay. So what does that tell us? Well, that means that this curve starts and ends at the same point and is contained within that plane, that curve is a boundary of some surface. And furthermore, it's the boundary of a surface that's sitting inside of that plane. And I can therefore write down the normal vector very conveniently just from looking at the geometry here. Right? Well, the surface is inside the plane. By the way, this surface, I could also choose this surface to be like bulging out of the plane if I wanted to, but why would I do that? It's much easier to choose a nice, easy surface. Right? Choose any surface you like whose boundary is that curve.
So you can use the same normal vector of the plane to define
the surface? Because the surface is in the plane.
Oh, okay.
Yeah, it's part of the plane.
That's why I was confused about my normal vector. I wasn't sure what to write down.
I see. So I can use 0, 1, 0 as my normal vector.
Would it be 0, 5, 0?
No, it's 0, 1, 0. The y coordinate here is 5, but the normal. Remember, the unit normal vector is a unit vector pointing perpendicular to that plane, and it doesn't really matter where that plane is. The normal vector is still pointing in the y direction. Yeah.
You cleared up one of my questions because I thought like
okay.
0, 5, 0 to divide it by like the magnitude to get like.
So you're thinking of what you would do on a sphere.
Probably.
Yeah, because you would do that on a sphere of a certain radius, but this isn't a sphere of a certain radius. This is just a plane.
Okay.
Yeah, so unit normal vector, unit vector pointing in the direction of y. That's this guy. So anyway, let's wrap up this problem, though. We're computing a line integral around this curve, f dot dx. Well, we just agreed that this curve is the boundary of a surface. So therefore, I can view this as flux of curl of the field through the surface itself, and there's my surface. I like that surface. And then dot the ds vector, which I'm going to write as normal vector ds scalar, just for because we're going to take advantage that we know the fact that we know what that is. Now let's compute the curl. This curl here. Well, okay, the vector field. All right, so we've got to play this game. So let's see, the curl is, the y partial of the third component is 0. The z partial of the second component is x. Okay, let's see, the z partial of the first component, 0. Love it. X partial of the third component, 0. Love it. And then let's see, the x partial of the second component is z. And then minus the y partial of the first component, which is x, so I have z minus x. So there's my curl vector, dot, here's my unit normal vector, 0, 1, 0. Again, ds. The integrand there happens to be 0, lucky break algebra, 0.
Thank you for your note. Thanks a lot.
Yeah, no problem. Okay, everybody happy?
Yeah.
Great, all righty.
Just a normal vector I was confused about because I got the result. I just wasn't sure if my normal vector was right.
Yeah. Okay, yeah.